All right, we'll get started. Okay, before we jump into the lecture, is there any questions about anything from last week? Okay. Okay, last class we talked about quick. This class I'm just going to go over the handshake sort of step by step. It was the one piece that we didn't do. There's a nice picture on Wikipedia that I'll pull into the notes. Okay, so this is a comparison between HTTPS and quick, HTTPS v2 and HTTPS v3. So this is HTTPS 1 and 2. And this is HTTPS 3, which is also known as quick. Okay, so this we already drew out, the whole handshake, although here it's sort of in abbreviated form. And some steps are combined in practice, so we kind of separated them out, but you can combine two steps. So the first thing you do is the three-way handshake, okay? So that's the TCP handshake. So 1, 2, 3. And then the server's ready to, or sorry, the client's ready to say hi. So they say, hello, I want to speak HTTPS. And the server says, great, here's my Diffie-Hellman key. Here's my certificate. And I'm going to sign this with the key that's inside the certificate. And I'm ready to talk HTTPS as well. Then the client says, here's my half of the Diffie-Hellman. Now we can both derive the same key, okay? So we both have a shared session key. So I'm going to switch encryption on. So change cipher suite means turn encryption on. And the finished message, remember, is a MAC over all the negotiations that happened in the protocol just to stop downgrade attacks. Okay, so this is a MAC, and it's, I'll say, anti-downgrade. Server says, okay, I'm turning on encryption too, and I'm done. So here's my MAC as well of everything that I saw of the conversation. They both check it, and then you're finally ready to start sending data. Okay. So it's sort of 1, 2, message there and back, a message there and back, a message there and back, and now I'm ready to drop some data. Okay. So with quick, what we're going to do is we're going to try and compress that. We're going to try and make it go a lot faster. So in quick, what we could have, there's different configurations or use cases, but in the main configuration, we're just going to do one handshake, and then we're ready to send data right away. Okay, so instead of 3 back and forth, 3 round trips, and then data comes on the 4th round trip, it's ready on the 2nd round trip. So this is sort of like 4 round trips for data. and this is 2 round trips. Maybe I'll phrase it differently. I'll say 3 round trips before data. And then here, just 1. Okay, now it looks pretty simple. So we have this initial message, we have hello, we have initialize sent back, we have hello again, we have the certificate, we have fin, and we have data, but there's going to be a bunch of stuff that's happening here, basically to replace all the stuff that's happening between these two here. Okay, so let's just go through it kind of step by step. So every time we go in one direction, I'm going to call it a flight. So I'll call this flight 1, we'll call this flight 2, and then we'll call this flight 3. I'll just say the direction, and let me fill in the first line, and then I'll try and figure out the spacing of this. Okay, so the first flight is from Alice to Concordia. I'll write it as client to server. And basically, I'm going to drop a bunch of stuff, but I'll give you the main essence. Everything we do in this class will always be kind of a sketch of the protocol with the focus on the crypto details of it. So there's a lot of like fields that sometimes like we leave out, like nonces and version numbers. And if you look at like actual TLS records, you see there's like 20 different fields and things like that. But anyways, okay. So basically you're going to say, hi, I want to speak HTTPS 3. And what you can do is send your Diffie-Hellman contribution right away, okay, in the first message. All right. Now, is this first message encrypted or not? What do we think?
Yeah.
Why not?
Because you need data.
Okay, so we can't encrypt it if we don't have a key. And the whole reason we're doing this is to get a key. Okay, so this is pre-key. So we can't encrypt it if we don't have a key, right? Okay, now what Quick does, we mentioned it last class, is it actually encrypts it anyways. It just uses a key that everyone could know. So it's not a secret key per se. It's going to encrypt it with a key that's derived from something that's going to be sent in clear text. Okay, so this will be encrypted. I'll call it key 1. And it's going to be the PRG extractor of what's called the DCID and then salt. So this is client chosen. So client chooses it, random. And this just comes out of the spec. So depending on what version you're doing and things like that, you'll get the salt out. Okay. What's the point of even encrypting it if, so the contents will be sent encrypted, and then the DC ID will be sent in clear text with it. So I'll, sometimes for encrypted, we use kind of like a double square bracket. So I'll do it like that. So this is encrypted under this key, K1, and the DC ID is sent in plain text with it. What's the point of encrypting? If anyone, an adversary in the middle could look up the salt value, they see the DCID, it's right there. So basically you're just encrypting with 2 salt values. What's the point of even doing an encryption? So the answer is not a security. It's not meant to protect this from a man in the middle. In fact, you don't have to protect this because we're doing Diffie-Hellman. It doesn't matter. Man in the middle can see it. It's more about like trying to stop routers from doing deep packet inspection and trying to make like decisions about how to route things and things like that. So that's the main reason why this is done. Okay, so this is called an initial key. And yeah. Okay, questions about this? All right. Now, there's a slight alternative to this. Yep.
So he's gonna send a message, which is gonna be encrypted, right, with the G of A, right? And that's gonna be the key 1 after he puts it through a PRG and extract it?
I don't know if I explained it well. So this notation here, I'm sort of cheating, but it means encryption under key K1. So this is the message that's being encrypted, and this is the key that's using to encrypt it. Does that make sense? Yeah. Okay. All right. Now, there is a mode where maybe I've talked to this server before. And if I've talked to this server before, I can do things a little bit faster. What the server will give me is they'll give me what's called a resumption key, okay, or a ticket. And it's a secret. The server gives it to me. And what I do is I come back and on the first pass I say, you know who I am already. Here's my proof that you know who I am. I have this thing that you gave me last time. And based on that thing, we may be able to start shortcutting different aspects, okay? So if I have one of those, okay, so I'll write resumption I'll try and use green for resumption. So on the first connection to a server, I don't have it, but on subsequent connections, I may have it. Then I will also send that value, the ticket value. I'll put it in the encryption of this as well. So I'll write it inside here. So I'll have a ticket. And I will MAC basically everything here up to here. So I'm going to MAC the rest of the message. I'm going to use the percentage key. It's just something that we use in Mathematica. I don't know why, I just like it. But that just means like everything before it. And I'm going to MAC it with something called the resumption key, which is in the ticket. Okay. So let me try and write this a little cleaner. So I'm going to call this RK. I'm going to just write percentage. And then I'm going to note that all of this is under K1. Okay. So let's talk about these things. So this we call a resumption key. It was created by the server, so the server created it. Last time we connected. And then it's sent to us. So last time we did the whole handshake, we got crypto. Once the crypto was in place, it said, here's a key, a ticket. You can remember this for next time. And it's going to maybe let you shortcut some of the handshake protocol. Yeah. Mm-hmm. Yes, yeah. So hold that question for a sec. Yeah. Okay, so what exactly is the ticket itself? So what does it look like? So there's basically 2 options for it. There's what we call stateful tickets, and there's stateless tickets. Stateful means that the server has to remember something. Yeah.
So you mentioned that encrypted with a key that everyone knows, won't the resumption key be decrypted by anyone, then anyone can?
Yep, yeah. So far, the resumption key, I used it to MAC all of this. So I used the key, but I didn't just write down the value of the key yet. So this doesn't leak RK, right? The ticket may or may not. We have to see what's inside a ticket first. But you're right. If the ticket was just the value RK, then anyone could decrypt it. They could get RK, and then we would have trouble. Yeah. Okay. So a ticket could be stateful or stateless. This applies to the server, and it's just like, does the server want to keep memory about all the connections that it's made in the past, or would it rather just forget everything? Right? It gives you something, you come back later. So generally, servers would like things to be stateless. It's better for the server. You don't have to remember things. But there are some advantages to being stateful, and so you may choose to do it if the advantages outweigh the sort of disadvantage of needing to keep state. Okay, so in a stateful setting, the ticket will basically just be an identifier. Okay, and this will be a pointer to a database that the server has, so a server database. And what it will do is it will look up that entry, and from the entry, it will get the recovery key, and it will have expiration as well. Okay, so usually these things don't last very long, like days kind of thing, and it may have other information there as well. It might say something about Alice and the client and things like that. I'll just write etc. Okay, so the ticket is just an ID. They look it up, they get RK, and once they have RK, they can check whether this MAC is correct or not. And what does that tell them? What does it tell them to check whether this MAC is correct or not? They would, sorry? I didn't catch.
Okay, so in the ticket we have a column for RK, like in the table when you look it up.
Mm-hmm.
And then at the end of it all, the RK is used to encrypt with the MAC.
Yep. But what does that prove?
Well, I want to assume the RK on the table is going to be unique to the individual.
Correct. Yeah. So this, I should write this. It's random, unique. Everyone gets a different RK.
So it's kind of lets them know like who they are. Like, is it legitimate? Is this
Okay, yeah. So it proves that the client knows RK. They could have seen the ticket, and an adversary can write in a ticket's just a database ID. So the adversary could replace this with any value, right? But so what you have to do is you have to prove that you know RK. How do you prove that you know RK? Well, you could put RK in the message, but if I put RK in the message, then anyone can steal it because it's not strongly encrypted. So I need a way to prove that I know something without saying what it is. So normally, like with passwords, like if I want to prove that I know a password, I just tell you what the password is. Okay. Here, I'm going to prove to you that I know this RK value, but by putting this value in the packet, it does not prove. It doesn't reveal any information about RK itself. Yeah. So the server can check that I know RK, but it doesn't reveal any information to anyone in the middle. Okay. So the MAC is a little different. Normally we use MACs to make sure that nothing changed, that nothing was modified. Here we're using it more like a proof of knowledge of this key. Okay, so I'm going to write a note about that here.
So does that
Yeah.
mean that the client, the user, is also storing RK? Like
Yeah, exactly. So the client, I should write that. Resumption key, server created it last time we connected. I can say Alice connected. Alice remembers it. So It's a shortcut for Alice for the next time, yeah.
So it's gonna check the RK in the ticket and the RK in the map?
Sorry, say it again. So
So you put it in the ticket also, in the ticket ID, you said there is RK expiration, etc. So that RK is the same as with the map?
yeah.
That's
So
how it's checking the authentication? Like
exactly. So let's complete the loop. The server grabs the ticket. It says, okay, I'm going to look this up in my database. And the server says, I have an entry. So that's good. The entry I have has an RK value. Now I want to check whether the client's RK is the same as my RK. And so I'm going to check that MAC. Okay. So this is proof that the client knows the value RK. Okay. If it's expired, then you just won't be able to do all the stuff in green. So you won't be able to resume your session. You'll have to do the stuff in black, which you can always do anyways. Yeah. Okay. Now there's a stateless option. A stateless is server doesn't want to keep a database. Okay. So if the server doesn't want to keep a database, what could it do? Drop.
Like, remove it.
Okay, so it could get rid of the database, but it needs to know whether it needs to get the RK back from the user. Yeah. Basically, it wants to get this information back from the user. So the naive thing is I could set ticket to be this information. Now I don't have to keep a database anymore because the ticket is the database entry. The problem with that is that RK now everyone knows. Okay? Right? So what can I do instead? What I can do is I can encrypt it for myself. Okay, so I'll encrypt basically this information. So I'll encrypt the database information. And I'm going to encrypt it with a key that belongs to the server. Okay, so the server gets a ticket. It says, I'm going to go get my key. I'm going to decrypt it. And then when I decrypt it, I'm going to see an RK, an expiry, and et cetera. Okay, all encryption that we do from now on, I'll note, is authenticated encryption. So if this got modified or something like that, it has a MAC built in. So think about like either encrypt MAC, MAC then encrypt, or GCM mode AES. Yeah.
So I'm guessing in the previous session the server gave you three things: RK, expiry date, and server key.
Yep. So you'll get the payload in here, and then you'll get the ticket itself. Yeah. And so what Alice will do is she'll remember all of it. So she'll remember the ticket, she'll remember the expiry, the RK, and things like that. And then she'll drop the ticket in. Because she has RK, then she can MAC the rest of it with it.
And this gets stored in the browser window, or I'm guessing it gets stored as cache.
So the browser will store it sort of like how it stores cookies and things like that. So it has a place now for this resumption stuff. And even actually in TLS 1.2, like the old TLS, we didn't do resumption, but there are resumption options there as well. But yeah. Your browser will store it automatically and it will remember everything. And then when you're about to make a new connection to a server, it will quickly go through everything it remembered and it will say, okay, is there a match? And then if it sees a match, it will drop this stuff in automatically, yeah. Okay, we're good so far? Yeah.
Sorry, can you please restate what Alice is remembering or the client and what the server is doing?
Yeah. Okay. So the server let's start with the server. So the server state, they either remember this information or they don't remember anything. That's good? Yeah. And then on the client side, let me write it up top. All right, so we have the DC ID that goes along there. Okay, I'll call it flight 0. So this is like before we fly. And this is on the client itself. What the client knows is it has a resumption key, it has a ticket, and then it knows whatever else, like the expiry or other stuff that it needs to know to decide whether to use it or not. Yeah. So this is it stored in the client browser. And it's only for resumption. It's only if you're reconnecting. So only, let me put that in green because we're kind of using green as the resumption part. Okay, it's good. Yeah.
So can we assume that when something is stateful, it doesn't necessarily mean this. Stateless doesn't necessarily mean the server is not storing anything, but it's just storing like a tiny bit of it. And for the stateful, it's like a verbatim version of the information it needs to remember.
Yeah, usually stateless means you're storing absolutely 0. So basically,
Is it now comparing with here in this case?
sorry, say again.
Like what is, because in the stateless you said that like Alice has to remember like the RK or the expiring, but the RK has to remember something, the ticket,
Yeah.
and then the server needs to be sure that what Alice is giving is actually genuine, like it's for Alice. It has to compare with something, or how does it know it's genuine?
Yeah. Sorry. So okay. So it does keep one piece of information, which is its key. Yeah. And so the trick here is that if the ticket were fake, then when we would try to decrypt, it would fail. And then it would fail. Then that's how I'm recognizing. So it's a good question. I'm glad you brought it up. The reason I'm recognizing that this was something I handed out in the past is because I can decrypt it with my key. And so I must have handed it out. Does that make sense? Yeah. Okay. So let me write that in. So if it decrypts, the server created it. Okay. And so you see this a lot, like say with cookies. I set a cookie value and I want to know I created that cookie value. What I'll do is I'll in this case, I don't have to encrypt it. I don't care about confidentiality. But what I'll do is I'll just MAC it with my key. Then when it comes back to me, I'll MAC it again and make sure that it matches, kind of thing. Yeah. So people will do this a lot. Yeah. So here, both the encryption's important. Otherwise, RK leaks, right? And the MAC that's implicit in authenticated encryption is important because that's what guarantees that this. It's almost like the server signed something, gave it to you, and then when you come back with it, it sees that it signed it. Yeah. So it's sort of like the server knows it created it. Okay. Yeah. Good. Other questions so far? Okay. All right. So this is a lot, but we packed it into one message. Okay. Now on flight 1, we can also do something else, which is because we have this RK value, sorry, we can do something else only on resumption. Okay, so if we're not resuming the connection, then we're going to wait for the message to come back. But if we're resuming, what we can do is we can actually just start sending data, and we're going to effectively encrypt it with the resumption key. So the resumption key is a secret that I have between me and the server, and so I can just start encrypting data right away. Okay, so we call this early data. So I can start sending packets right away. They'll be encrypted with, I'll call it K2. This is called early data because we're sending it before we did the handshake. Okay, and the encryption that we're using, K2, is going to be derived from the resumption key. So we don't generally use the resumption key directly, and normally we pull out two keys, one for one direction and one for the other direction. I'm sort of simplifying these details, but anyway, so we'll use the resumption key to start encrypting data. Okay, now there's one problem with this. Okay, the problem with this is that if I see this packet go by and I'm an adversary, I can replay the ticket and I can replay the MAC, right? So the MAC doesn't, it proves that the person who created the MAC knows RK, but if I see that, I can replay it, and then even though I don't know RK itself, okay? And if I replay it, then the server will just go and say, okay, I see this RK, or in the stateless case, it will say, decrypting this ticket, and it is that RK. I'm going to check the RK that I get out against the MAC, and everything is okay. Okay, and then what I can do is I can even replay these packets, okay, because they're going to be encrypted under the same key itself. Okay, so there's no replay protection against this. So because of this, some servers will not accept early data. Okay, some servers will. Well, actually, no one's going to just unilaterally accept it. What servers are going to do is they're going to look at it and they're going to say a couple things. The first thing is they might decide based on what kind of packet it is. Okay, so if the packet is just like give me index.html, that's usually the first thing that you would ask for. It might say, who cares if someone wants to replay that? Then the server's just going to send index.html to them and they didn't ask for it. That's not like critical security. Yeah. So if it's some sort of GET request or something like that, that's fine. On the other hand, let's say it's like I'm posting my credit card because I'm purchasing something. That's the kind of packet that you might not want people to just arbitrarily replay. And so what it will say is, I'm going to reject that at this stage. You can send that packet later, but after we do the whole handshake. The other thing the server might do, this is stateful, is if it's stateful already, what it can do is it can just remember whether this has been used or not. Okay? So it can add a little flag that says this is, and basically the first person, the adversary won't be able to replay it until they have to see the ticket value and the RK value. So they would have to wait until they see it. So the first time this gets sent, the server will accept it, but then they'll set a flag here that says, I've already seen it. And then if I replay it a second time, then the server will reject it at the second time. Okay? But the problem with that is that the server does have to remember it. And the other thing a server can do is just delete it. So the first time it's used, once it's done with it, it just deletes the database entry. And then the second time, if someone tries to replay it, it'll just be like, I don't have an entry for that ID. It looks like a fake ID. Okay. And generally, what's the difference between these two? So most servers would like to be stateless, because why keep a database if you don't have to? Okay. The problem here is sometimes you want to do what's called revocation. So you hand out a credential to someone and you want to get it back. You want to cancel it for some reason. I don't know why. Maybe your database of RKs leaked, or you realize there was malware on the machine when you handed out all these RKs. Okay? So an adversary knows them. If it's a database, you can just delete the database entry and now it's revoked. If you've handed something out to someone, you can't get it back. It's in their possession. Okay? You could write down a list to yourself, and then every time stuff comes back, you can check it against the list and say, oh, I want to revoke that or not. But it's a lot easier to revoke something that you have possession over as opposed to something that you put out into circulation. Okay? So that's why people might prefer stateful to stateless, is just for revocation purposes. Okay. Yeah.
Can we say like the way you just said, like more secure in a way, like there is more pros to using a stateful like approach than stateless, because it gives you like basically like audit trail in a sense of what has happened, and probably like you said, you don't like kind of relocate like access to something or say okay, this was when this happened, like an audit log, activities.
Right. Yeah. I think generally stateful is better from a security posture, but stateless is better for performance. As soon as you see it, you know what it is. You don't have to look it up in a database and things like that. Yeah. And if you have millions of users, stateless is going to make a difference, like a tangible difference. Yeah. Yeah. So you can think of it as sort of security versus performance. Okay. So early data. By the way, this key, sometimes we call it zero round trip time key. So 0 RT. Okay, so I'll add here, this is vulnerable to replay. So servers will do one of two things. They'll check out what the packet is, and they'll decide if it's sensitive to replays or not. Okay, so they'll inspect packet and accept if replay doesn't look serious. So like a GET request would be a good example of something that you might accept. Post or something like that might be something that you reject. I'll just write and or, so you might do one of these or both. Or none. The second thing you could do is just keep track of tickets. And accept only once. So if you're stateful, that's easy. You just add a field here of whether you've seen it, or you just delete it when you've seen it. If you're stateless, you can still, and now you don't have to store everything about the ticket, but you will just remember all the tickets that you've seen. So you might have a list of all your recently seen tickets. You could use a data structure like a Bloom filter or something like that to make it very efficient. But anyways, it's still going to be a lot more efficient than doing full stateful things. Okay. Or you might also just like not accept. You might just reject early data. So there's lots of servers out there that just don't allow early data, period. Yeah. So you could, the replay could happen as fast as the adversary wants. Like, so if I see the packet go by, I can replay it instantly, like 1,000 times or something like that. You could use like really short windows, but then you're kind of trading off like how easy this is for resumption, because now if I wait too long to resume, then it's done anyways. So I'd say that like timing doesn't really help. Yeah.
So
Yep.
Professor, if we keep stateful, then we can create a memory task, and if it's stateless, then we can create a computation task. So
Well, so if it's stateless, correct. Yeah, so you do have to decrypt this. So you're running a decryption, so that's,
computation.
yeah, so it's going to cost something in terms of computation itself. Yeah. Decryption, though, in my mind, decryption's free.
Yeah, it doesn't take much computation, but still we can consume some CPU. But stateful is we can consume lots of memory.
Sure. Yeah. So if you're going to achieve stateless, it's a good point. So if you're going to achieve stateless, like securely, you're probably going to use cryptography. And that means when you see tokens, you're going to be decrypting or checking max or that type of stuff. So it's true that you are trading off storage for computation. But the overall, like I say, crypto operations usually do in hardware 1 clock cycle. So you don't even consume CPU time really from it. And so this was not always the case. So like in the, like say the 90s or 2000s, like this was a big issue and people didn't want to turn on encryption. But by today's standards, it's virtually free. Yeah. Okay, other questions? Yeah.
I just want to confirm. The replay attack,
Yeah.
is it the same as saying it doesn't give you forward secrecy?
It doesn't give you forward
Secrecy.
Yeah, forward secrecy is different. That's like when this key gets leaked. It's when I record what I see today, and then say I get malware on your machine a year from now, and I get your key. Can I decrypt all the stuff I stored for the past year? If the answer to that is no, then it's forward secret. And if the answer is yes, then it is. Yeah. There would be no forward secrecy on this. So if I get gay 2 at some point in the future, I can decrypt these. Yeah. But when we're done, when we do the whole handshake, then the new key will have forward secrecy because we're doing Diffie-Hellman. Yeah. So I can write that in too. It's another point too. So if you care a lot about forward secrecy, then you might not want to do this as well. It's another reason to reject it. Okay. So that's flight 1. So we send this stuff. If we're resuming, we send this as well. And if we're resuming, we can also send packets right away. Okay. So in this diagram, we're actually sending data. We're sending initialize, hello, and data all in the first pass itself. Now, normally, even if you do early data, the reason we call it early, not final data, is we're still going to do the handshake. And what the handshake's going to do is it's going to give us a new key, and then we'll mix the new key in with the old key. Okay? If we mix them together, then we get a key that's sort of the best of both worlds kind of thing. So we're still going to continue doing the handshake even if we're in resumption mode. Okay? So we'll go to flight 2. So this is now what the server is going to say back to the client. Okay, so it's just going to say hello back. It will do all the cipher suite version numbers, all of that negotiation. And it will send its Diffie-Hellman component. And all of this we're going to encrypt under K1, which we've already seen up here. It's the same, the not secret key. Okay. Okay. Then what it's going to do is it's going to send its certificate. Now, this is in the same flow, okay? So it's sending it in the same flow. So why did I split it out? Why don't I just add certificate here? Well, once GB reaches the client can compute G to the AB, and the client can then, they can now have a new key, okay? And so what I can do is I can encrypt everything after G to B gets sent, I can encrypt under that new key. And so I might as well, it's going to be a stronger key than K1. K1 is basically no key at all. So what I'll do is I'll send the certificate encrypted under the new key. And so we'll call this K3 because we had a K2 here, which was the resumption key. Where do we have it? Right here. Yeah. So we'll encrypt this under K3, and it's just going to be the PRG extraction of G to the AB. Okay, and then we're done at this point. So now we have K3. K3 is our good key. And so we're ready to switch on encryption, like change cipher suite. And we can take a MAC over the negotiation to make sure there's no downgrades. In Quick, we just combine that into a finished message. So it's kind of like the finished message in TLS2, sorry, in HTTPS2. It's like this message here, except for it combines CCS and FIN. Okay, the only other thing that you might see happen here is if you're resuming, then you already know the certificate. Like I connected to them before, we did the whole handshake, I know what their certificate is. They gave me this resumption key. I'm coming back to them. And so I've already checked out their certificate and things like that. I'm happy with it. So I don't need to see the certificate again. Okay. So if we're resuming, we can skip sending this. Okay. And the certificate's kind of big, so we'd like to skip that. We don't want to send it if we don't have to. And usually it's not just one certificate, it's like a chain of certificates back to the root. Okay. Then okay, what will happen then is the client will send to the server a finished message as well. And it will send it with K3. Okay. And then now we're ready to send data. And so it can also just start sending data, not early data, but late data. So it can send packets. And here it's going to use either K3. If it's a brand new connection, that's all it knows. Or if we're resuming, what we're going to do is we're going to, because we have this resumption key anyways, we're going to mix it in with the Diffie-Hellman and make a K4. So this is only under resumption, but K4 will just be the PRG of the extraction of G to the AB and the resumption key kind of mixed together. Okay. Now, this here, we sometimes call a ratchet. So what we're doing is we have some old key material, and we did a new, say, Diffie-Hellman. Now we have a new key, and what we're going to do is we're sort of going to combine them. And now we have a new key. And ratchets are useful because let's say some of your keys get compromised. Every time you do a new Diffie-Hellman and mix it in, you kind of recover the fact that like you get a new key essentially that the adversary doesn't know anymore. So if an adversary attacks at a certain point, they can decrypt all of your communication up until you ratchet, and then once you ratchet, then they lose track of the key again. Okay, so some protocols, Quick isn't one, but some protocols are based on like ratcheting a lot. Okay, so in a couple lectures, maybe at the end of this class, we'll see how far we get, but probably next class, we're going to switch gears and talk about secure messaging protocols. So we'll talk about email, and we'll talk about like instant messaging. And the best encrypted protocol for instant messaging is from Signal, and it uses ratcheting. It uses something called a double ratchet. It looks really complicated when you draw it out, but it conceptually hopefully isn't that complicated. But anyway, so we'll come back to this idea of ratcheting, and I'll define like what the security properties and stuff are there. But anyway, this is a concept that you're going to see again. Okay, and then yeah.
Ratcheting is, when you use the PRG with the extractor.
No, so by the way, this sometimes we're going to start calling this KDF soon. So we're going to just combine these two functions into something called a key derivation function. But ratcheting is just I guess it's confusing because the arrow's pointing at the extractor, but it's just the idea of kind of mixing two keys together.
Okay.
Yeah. So you mix two keys together, and then it's slightly more specific than this, but you'll see there's a certain like kind of format that you use. But you always mix two keys together, and then you pull two keys out. One key you use, the other key you keep kind of like as state, and then the next time you want to ratchet, you ratchet from that key that you kept. So you have this sort of like chain. We'll draw it all out.
K always stays the same.
Sorry?
The key you ratchet with always stays the same.
Both of these should change. So yeah, in proper ratcheting, what you would do is you would take in, say, J to the A, B, and RK. You would output two keys, a new RK that you're going to use next time, and you would output a key that you want to use right away, like for all your encryption and things like that. And then the next time you ratchet, you'll take the RK that you have now, and you'll combine it with your new Diffie-Hellman, and then you'll keep going. Yeah. Yeah, no problem. So I can sort of draw the picture, but so I'll call this a KDF here. This we sometimes call a chain key, just something that you remember. And so when you do a KDF, you put in the chain key, so that would be like what RK is. You put in your new Diffie-Hellman, and then you're going to get out a new chain key. And you'll also get out a key that you can use for encryption and decryption at that epoch. So this is the key that you're going to use. And then if you ever want to do Diffie-Hellman again, you take this in, you run it through the KDF with your new Diffie-Hellman, and then you get out a new chain key that you remember. And then you get a new key that you can start using. Yeah. And as long as both the sender and the receiver know the chain key, and they're both going to be able to derive this by doing Diffie-Hellman, they'll be able to follow. So both the sender and receiver will go through this sort of chain. And then once you have chain key 3, you throw away chain key 2, you throw away chain key 1, and you can't go backwards. So a KDF doesn't let you go backwards. It's kind of like looking at the output of a pseudo-random generator and guessing the seed. We know that you can't do that. So because you can't go backwards, if the adversary breaks into my computer and steals my key here, all my messages that were encrypted under the things previously are secure. Okay? And once I do a proper Diffie-Hellman again, then all the messages after will also be secure. Okay? So I'm only vulnerable if they steal chain key 2. I'm only vulnerable in the time between I did these two things. Yeah. So you could, like an extreme, let's say you're doing Signal, you could ratchet on every message. So every time I send you a message, we do Diffie-Hellman, and we just continuously do it. Sometimes you send more than one message before the person receives them because they're offline, and so they you won't quite ratchet at every message, but that's the sort of the concept of it. And so if your device gets broken into at a certain point, someone steals the key, they can't decrypt all your past communications, and they're not going to be able to decrypt your future communications once you re-ratchet. But anyways, we'll get there later. So I'll say C signal later. Okay. Any questions about the handshake? Quick handshake.
I have a question
Yeah.
from the above.
Yeah.
Why you need forward, like you say, no forward secrecy, but I don't think we need to even establish forward secrecy at that point.
Yeah. So thanks for reminding me. I will just, I want to note here that we do have forward secrecy here. Now that you brought it up. So the only thing, we wouldn't have it on the early data, but then we'll have it on
Yeah,
the,
because nothing has been established within, only client is asking server to authorize and find that, like, allow me.
correct.
So if there is, even though if they say like, okay, this is the older message in the ticket, it get it the RK from there, it doesn't really matter because the connection hasn't been established. So until the handshake hasn't been done and the server hasn't been authorized, even though you replay the attack and you get the key, it doesn't really matter.
Correct. Yeah. Okay. So let me just summarize what you're saying, and then I'll answer the question. So early data is happening on this first flow. Okay. Because we haven't heard back from the server, we can't possibly negotiate a new key because we haven't heard back from the server. And so also, what can early data be? It can't be a back and forth conversation, because if it's a back and forth conversation, then the server sent something back to me. Okay. So early data by definition is only things I'm sending to the server before I hear back from the server. So typically that would be just like, get me this website, that kind of thing. Yeah. But once it sends the website back, then it will also send all this handshake stuff back. And then the next time when I say, okay, I got your website, I want to get the next thing, then we've already finished quick at that point. Okay.
That I think at the flight 1 and
Yeah.
0, it doesn't really matter if you have forward secrecy.
Okay, so forward secrecy means I steal your key, or sorry, I don't know your key today, but I'm interested in the kinds of things that you do. So I'm just writing down everything you do. And then a year from now, I get malware on your machine, I steal your key. Okay. It's true that you would only be able to decrypt that initial message. You won't get any of the back and forth. And whether that matters or not depends on whether you think this is sensitive or not. Yeah.
Because the initial message is what you may have taken as an older client, but that thing was also old.
Okay.
But it doesn't really inherit any property what will impact my security from previous messages.
So the initial packet that you send here without the thing without forward secrecy, it is a new packet that you're sending to the server. So I'm going to say Concordia, and I'm saying give me index.html. That's the packet that I'm sending. That's the packet that won't have forward secrecy. So I could learn that you asked for index.html. I won't know what the website sent back, and I won't know anything else about what you talked about.
That's why it's a general information you could take anyway.
Possibly, yeah. So you'd have to drill down, I guess, and think about, is that first message that you asked for ever sensitive? Yeah. I could think of scenarios where maybe it would be, but like if you're going to a website and like I learn what page you're looking for on that website.
It still depends. I can learn that you can learn what pages I have been searching, but it only matters if you get authentication as me to reach out to that page. You can learn whatever people are searching because that's not a secret.
Correct.
But it only matter as integrity, as authentication, once you get authorized to actually go to that page as a user.
So that depends on the kind of page that's being served. So there are pages that are served like not to everyone. So different people would go to the same website, they get different responses. An extreme version of that would be I have to log in. So like I'm asking for my inbox. What you learn is just that I asked for my inbox, but you don't know. I can ask for my inbox, but it's going to be different than your inbox, kind of thing. Yeah. Where this could be, it's not really that dangerous, but like the example I use in another class is, let's say you're going to Wikipedia. I know you're going to Wikipedia because that's on the outside of the connection, right? But I don't know what article you're looking at. If I'm able to decrypt this first packet using early data, then now I know what article you asked for. And if somehow that's a sensitive article, like in a certain country or something, then that could be problematic.
Could be illegal content you want to reach, which is actually prohibited to use in that specific country.
Exactly, yeah.
But then they cannot still prove it that it was, because it's not authenticated by me. It could be I may have tried to go to that page, but there is still, but so like.
Proving's a different thing,
Yeah.
yeah. So like usually with intelligence, they want to know what you're looking at because they're investigating you and they want to know whether they want to bring you in for an interview or something.
Like one
But
question,
yeah.
you don't need a forward secrecy at flight 0 and 1.
Okay,
We have written that not forward secrecy, but we don't even have to consider it.
but in the example of Wikipedia, right? If I send my requests for the website as early data and my key gets compromised in the future, you as an adversary are able to learn it because there was no forward secrecy. If I waited and send it in flow 3, the same threat, you get my key later, you will not know which article I looked at. Yeah? So there is a difference between the two. So forward secrecy, I think, is relevant to that.
Sir, by forward secrecy, you mean key exchange, right?
So forward secrecy just means an adversary writes down the cipher. They can't decrypt it today. They're writing down all the ciphertexts. But then a month from now or a year from now, they get your key. Can they go backwards and decrypt everything that you looked at or talked about? Yeah? Now, the forward secrecy also usually doesn't apply to session keys like RK. So RK here is kind of like a session key. It's usually more of a long-term key. But anyways, I take your point. It's sort of complicated, but I do think it's relevant to note that it's not forward secret,
Sir,
but not that critical.
You
Yeah.
explained this when you showed us an example of the cipher suites.
Yeah.
It was
Yeah.
written like FS.
Mm-hmm.
It's the same, right?
Exactly. Yeah, it's the same thing. Yeah. So Diffie-Hellman, you always have forward secrecy, and here because you're basically just using a key right away, you don't have it. Yeah. Okay. Other questions or points? This is all I want to say about Quick. So now's your time to ask questions about it. Otherwise, we're going to move on. Okay. All right. So next thing I want to talk about is the last thing. So there's two other kinds of secure tunnels. So far, let's just sort of take a recap of what we talked about. So we talked about secure tunnels. So we talked about TLS as kind of the base. Then we talked about HTTPS 1 and 2. And then we talked about Quick, which is version 3 of HTTPS. In order to motivate the man-in-the-middle attack, because that's what a secure tunnel protects you against, we also talked about like BGP hijacking, that kind of thing. And then because Quick runs over UDP, we had a brief discussion of DOS amplification attacks, which is something that you don't really have to care about when you're running over TCP, but once you run over UDP, then it becomes an issue. Okay, so there's two other kinds of secure tunnels. I want to show you a fancier one. So we're going to look at Tor. So this is like an anonymous web browser. And then related to Tor is VPN. And VPN, I'm going to save until later because even though it's a secure tunnel, usually you're doing it because you want to get access to something within an organization. And there's going to be like 100 protocols about, like, once you prove that you're an employee of Concordia or a student at Concordia, now I can give you that library, that paper, that academic paper that the library pays a subscription to, or I can give you the textbook for free or whatever, okay? So there's going to be a bunch of things about, like, how do you prove that you're a student? And then once you're a student, how do you do that authorization? VPN kind of fits into that. So we'll circle back to VPN later.
Could it also be like within a government building to access like the network there? It has to be within VPN.
So a VPN gets you onto a corporate network, or like a private. So it could be a corporation, government, university. When you're not on that network, and then once you're on the network, then you'll presumably the reason you're VPNing in the first place is so that you can so that you get access to things that are not available to anyone who's outside of the network. Yeah. Yeah. So it's like an intranet. Yeah, for the company. Yeah. Yeah, okay. So there's sort of like two, this sort of goes into Tor, but there's two use cases of VPNs. So the reason they were created in the first place was for like employees working abroad and things like that, and they want to connect into the network. But there's another story about VPN, which is people use it to geo-hop. So I'm in a network, and for whatever reason, I don't want to be in that network anymore. So I'm going to hop over to another network. So it could be government censorship of the internet. It could be that I just want to watch some BBC show for free. And so I want to.
Anonymity.
And then it could be for anonymity as well. Yeah. And then Tor, what it does is, Tor is like a VPN in that sense, but it's a stronger kind of version of a VPN. Okay, so anyways, we're going to save VPN for later, but I'll say a bit about it to motivate Tor itself, but right now we're going to talk about Tor. Now I cover Tor in another course that I teach, more like the usability of it and like how to use it. Right, in this class I'm just going to cover the crypto itself, but yeah.
I was going to ask, does proxy, do they like kind of relate with the VPN scenario you just mentioned?
Yeah, absolutely, yeah. So let's, let me get there in a second. Yeah, okay. So what does Tor do? What it does is it hides your IP address. How does it hide your IP address? So you could imagine two things if you don't know anything about Tor. One is it just somehow drops your IP address. So now you have packets going around and there's no IP address. Unfortunately, that doesn't work. The packets won't get delivered, like they can't come back to you if there's no IP address, okay? So what Tor is going to do is the same thing as a VPN or a proxy, which is there's going to be an IP address, it's just not going to be yours. So you're going to put someone else's IP address in for your IP address. Then the packets are going to go to that person, and then that person's going to send them to you, okay? So it hides your IP address. How? Basically, it's going to substitute it with another node's IP address. Okay, now you're going to say, okay, this sounds like a VPN. Or a proxy. What's the difference between a VPN and a proxy? So they both work essentially the same thing. VPN has a different protocol. It can use actually TLS. They could end up using the same protocol, but VPNs are more like a corporate tool with its own protocol. A proxy is more like a basic web protocol. So they look slightly different, but because VPNs are so widely deployed and proxies, you have to go like mess with your browser settings to set up a proxy. VPN, you just download the software and run it. And VPNs it's easier to suck in data. So a proxy, usually like you could set it up for your browser, but VPNs would be like your whole operating system. So all data goes through the VPNs. So people who want to use proxies usually just end up using the VPN protocol itself. So proxies are kind of dead at this point for this reason, for anonymity or geo-hopping. Yeah.
I said because of usability issues.
Yeah.
Now we assume that like VPNs are practically user friendly because they're really doing so much tinkering you have to do as a user. You just like kind of get it and switch it and just works.
Correct. Yeah. So it's easier and you're less likely to make mistakes with it. Yeah.
But VPN is also related. VPN is with the certification also, right? But proxy does not.
So the certificates and stuff, they would look the same. So like there's the only real difference between them is just the protocol that they run. Yeah.
Because if I'm using my corporate laptop
Yeah.
and it has the VPN,
Yeah.
so it does relate to the certificate to that VPN.
Correct. Yeah. So there's two things. Let's draw a little picture to just talk about this. So I'm basically going to have something in the middle, and then I'm going to have the server itself. So we'll call this Concordia. And here's Alice. And then here's our VPN or proxy. Okay, so with VPNs, with a proxy, Alice needs to know that she's talking to the proxy. So what she wants is she wants to have a secure tunnel to the proxy. So she's going to need the proxy certificate or key in order to know that she has a secure tunnel to the proxy. Okay? VPN's the same. So you also want to have a certificate to identify this endpoint. But VPNs are often paid services. And so they may want to authenticate the client as well. So they might want the client to have something to identify themselves. It could be a username, password. It could be a certificate. There's different ways of setting VPNs up. But you might actually have mutual authentication in the VPN case. With proxies, not typically. Yeah. And then you'll have hopefully a secure tunnel. I'll just draw a little lock. Actually, I'll draw a tunnel because that's what we've been using. Hopefully you would have a secure tunnel between the proxy, VPN, and Concordia, but you actually have no idea whether that's happening or not because you can't see it. Once it leaves, all you know is I have a secure tunnel to here. I'm putting my traffic onto this thing and it's sending it on my behalf, but I don't know anything about what's happening on the other end.
So when we do the VPN connection also, it always show a lock with the connection also.
Yeah. So the
The tunnel is TLS?
actually, okay. Let me correct what I said. What I said was wrong. What you'll end up with if you access a website over a proxy or a VPN is you'll actually get what you want. You'll get a tunnel inside a tunnel. So you'll have an end-to-end tunnel to Concordia, and it will just be kind of inside the tunnel here. So
It's an extra layer of encryption.
yeah. So you'll have and you may, if you're using a proxy, you might not even have a secure tunnel between you and the proxy server. It depends how the proxy, but with VPN, you'll have a tunnel between you and the VPN. And then if you're doing HTTPS, you'll have a tunnel end-to-end to the server. And if you're not, you won't have that. Okay, yeah.
Sorry, in the case of the proxy, is there anybody keeping logs of where you are going?
Yeah, absolutely. Yeah, so they can keep a log. First off, they have to keep a log because let's say I go to Concordia and Concordia responds, they have to get that back to me. So they have to know who was it that was accessing Concordia. So they will keep a log at least temporarily just to do their job, but they could keep it long term. And what happens if someone gets the log? Then you don't have anonymity anymore. Yeah. So the anonymity depends on not keeping a log. Okay. Other questions about this?
The type of encryption is TLS
Yeah. So the this
and VPN and proxy.
this is HTTPS. This is a VPN. So if it's a proxy, it would probably be TLS. If there was any encryption, or it would just be HTTPS. If it's a VPN here, you have basically, there's three kinds of encryption. So there's one that's based on IPsec, there's one that's based on TLS, and then there's one called WireGuard. And so WireGuard's the best, but it depends, different
So that's
VPNs.
the difference. As you mentioned, that the difference is only the protocol, right?
Yeah, exactly, yeah. So VPNs, and you need custom software. I guess that's the other difference. So here, because your browser doesn't speak VPN, you're going to install a VPN client.
Yeah.
With a proxy, you can just type in all the information about your proxy, and then it will just go. Yeah. So like, if I have a computer, I'm really indifferent between using a VPN or a proxy. But let's say I have my Apple TV. My Apple TV doesn't let me run a VPN, probably, right? And so I'm kind of stuck. But I could do a proxy. Like, it would probably have proxy settings, and then I could do it. But they do basically the same. Yeah. And then the reason we have them is it's more different use cases. So VPNs were more the corporate use case, and then proxies were actually for this picture. But then because VPNs sort of do this anyways, everyone just started using VPNs for this. Yeah. So in general, you can kind of forget today that proxies exist.
Yeah.
Like they basically are obsolete with VPNs. Yeah.
I think on the VPN, I'm not sure if you can put restrictions also.
Sure. There, yeah, of course. Yeah, you can put lots of stuff.
Not in the proxy.
So in the proxy, it depends what the server can see. So the server's in the middle. They can make any decision they want. So they can put any access control policy they want. But with the VPN, if you're pulling authentication information off the user, then you could have like roles that are attached and things like that, and then you would have more information to make decisions with. Yeah. Okay, other questions? Okay, good. Let's take a 10-minute break, and then when we come back, I'll show you what Tor does differently. Okay. All right, Tor. Okay, so we have this picture of a VPN proxy. The main vulnerability right here is the proxy itself. If you care about maintaining your anonymity from an adversary, what the adversary can do is try to get the log or just be a bad VPN or proxy that's tracking traffic anyways. Okay, so what Tor is going to do is it's going to be exactly the same picture, except for what we're going to do is we're going to basically go through like 3 of them instead of 1. Okay, so we have Alice. We're going to have like a proxy, we'll call it a node. Okay, and we'll send traffic through 3 of them. Traffic will come back through them. 3 is an arbitrary number, so it's the default if you use Tor, but you can make it 1, you can make it 2, you can make it 10, totally up to you. Why is this a better picture than this picture? Okay, so the reason is in this picture, although they might keep logs still, the adversary would have to compromise all 3 of them. This is the property that we want anyways. We have to make sure that cryptographically we can make it so that the nodes don't know about other stuff, but we'll talk about that in a second. But here the adversary just has to corrupt 1 server. Here we would like to get all 3 of them. Okay, now yeah.
So if he knows just the first one, he wouldn't know where that packet going, but he would know where it's coming from.
Yeah, so if he's node 1, what we want is node 1 will know that it's receiving from Alice and it will know about node 2, but it's not going to know about node 3 or Concordia. Yeah, node 2 will know about node 1 and node 3, but it won't know about Concordia or Alice. And node 3 will know that some user is sending stuff to Concordia, but it won't know anything about node 1 or that it's Alice. Okay. Okay, so that's sort of the picture that we want. Okay. Now, what if Alice sends a packet that says, okay, node 1, send this to node 2, node 2, send this to node 3, node 3, send this to Concordia. If node 1 can just open up that packet, it can see the whole chain, right? It knows it's going to node 2, it knows it's going to node 3, it knows it's going to Concordia. And so in this case, it's pointless to add extra nodes on the end, okay? So what we need is we need to make it so that node 1 can only inspect the packet deep enough to know it's going to node 2, yet the packet needs to have instructions to go to node 3 to go to Concordia, okay? So what we're going to do is we're going to kind of nest encryption inside of encryption inside of encryption. And that's sort of the approach that we're going to use, okay?
It's a layered approach.
A layered.
And then another layer, and then maybe more layers.
Correct, yeah. Yeah. Okay, so let me draw the picture of Tor a little bit better, and then then I'll talk about what the handshake basically looks like. Okay, so we have Alice, she's a user, she decides she wants to use Tor. Where do these 3 nodes come from? So what will happen is she'll connect to Tor directory. So Tor runs a directory. And Tor's directory will tell Alice about all the nodes on the network and their public keys. Okay? So Alice will learn that there's a node here, there's a node here. Here's Concordia. All right. Then what Alice can do is she can pick any 3 that she wants from the network. Okay? So she'll try and form a path between them. So she might decide I'm going to use this one first, then this will be my second node, and my third node will be this one.
And who picks that?
She does, her client does it.
Yeah, but like to know which nodes there are, the Tor client will pick those?
Yep.
The actual browser?
Yep, so she'll download the software. So it will come down as a browser. That's the most standard way. You can also configure it just at the operating system. And that client will make the decision for her. You can override it if you...
This is random?
Yep. Well, sort of, it tries to, these nodes will be all over the world. So sometimes it will try to bounce it through different countries so you don't go through the same country 3 times. It's a little different than random. And it has some controls over the nodes, the entrance nodes as they're called, and the last node as well. So not every node wants to be an entrance node or an exit node. I'll talk about that in a sec. But okay, so the basic idea is I'm going to make a path through my 3 chosen nodes. And then this node is going to send it to Concordia itself.
It can be through only one node, right?
Yeah, if you want, yeah. Then it's basically a free VPN. You can think of it that way, yeah.
But 3 is actually, I think, a sweet spot for, trade-off of, being anonymous and also being efficient.
Yeah, exactly,
It's
yeah.
not that arbitrary.
Yeah. So the 3 is nice. Actually, so it reminds me of something I wanted to say at this picture. I'll say it in a second. But if you go less than 3,
Layer out encryption, but if you go more than 3, it's not that it's not adding that much, because if you actually know the nodes before, then you need the whole.
correct. And if you add more than 3, what happens as well? The performance goes down too. Yeah.
Latency.
Exactly. Yeah. Okay. So let me say 2 things. The first is I did talk about an adversary controlling 1, 2, 3. It's actually usually sufficient if the adversary can be somewhere between you and node 1. So that could be your ISP or something like that. And at the end. Now, if I'm here, either at node 1 or somewhere here and here, I see traffic going through, and I see traffic coming out the other end. I can't say for sure it's the same traffic because I don't know what's happening in the middle, but I can infer it's the same traffic just by looking at the shape of it. So it will be a certain number of packets of certain sizes at certain times, and then I'm going to see that exact same pattern or fingerprint of data come out here, you know, a second later, a millisecond later, or whatever. And so I can infer with strong probability that it's the same, that Alice is talking to Concordia. Okay, so we call this a global adversary, and basically Tor does not try to protect against that. It doesn't promise anything against a global adversary. But if you have a single adversary that's on one of these connections, then it should be secure. Yeah. Yeah, so you could VPN before you go to Tor, but it's the same as just adding a fourth node. So it doesn't really, you could also just go through 4 nodes and it won't, yeah.
But the nodes can follow the system of store now, decrypt later, that's right?
So sorry, say again,
The nodes can follow the system of store now, decrypt later.
correct, but the adversary would have to run all 3 nodes, or at least 2, the entrance and the exit node. Yeah, so by the way, you can assume that some of these nodes are adversarial, right? So these nodes, you don't know who's running them. They could be government, you don't know. And so the idea is by picking 3, I'm trying to hope that I get one good one at least. Yeah.
So I was thinking if VPN is system wide,
Yeah.
and you're connected to VPN from your Tor, let's say Tor browser, will the ISP know what is leaving your computer?
So the ISP will know what, it depends if you connect a VPN before Tor, it will know that you're talking to a VPN server. It won't know that you're talking about Tor.
No, like, will it know like the size of packets? Because
Yeah.
some VPNs encrypt like data from the ISPs.
Correct. Yeah. So encryption preserves length, and so the ISP knows the length of everything. Yeah. Okay. Now there's one option, one other option which we won't care about, but I'll put it in. Let's say you're in a country and it blocks Tor. So the country, like say the government, they can go get the Tor directory. Now they know all the nodes in Tor, so they can just block all the nodes, blacklist them. Okay, deny list them.
Or bridge.
Yeah, so what you can do is you can have another node here. I'll call it a bridge. And you can connect to the bridge first, and then the bridge will connect you into Tor. And the bridge is a node that's not in the Tor directory. Yeah.
That is what he's referring, like using a VPN or proxy. That
Sure.
solve the problem, right?
Correct, if the VPN isn't blocked. So the problem with the government is they could also just block VPNs. And it's easier to block VPNs because you can recognize the VPN protocol because it looks different. And so you can just block all VPN traffic, period. So you could just turn off all VPNs in a country if you wanted. If you know like nobody's using VPNs for the right reasons anyways. But yeah, it's the same idea. Yeah. Yeah. So what a bridge is it's a Tor node that's not in the directory, basically. Okay, so a bridge is a Tor node not in the directory. So it can't be blocked by the government if the government just goes through the directory and gets them. Okay. Now, if the government can't find the bridge IP, how does Alice learn what it is? So you're in a country, the internet's blocked, Tor is blocked. You need one of these bridge nodes, right? If I can figure it out as Alice, then the government can whatever process I use, the government could use the same process, and then it could find all the bridges and block them as well. Okay, so bridges are usually actually handed out by hand. So what will happen is like there'll be like a human rights organization in a country. They'll have a list of bridges. They'll be given by the Tor project, and then they'll hand it out to people they know, and then that's how they get circulated. The other way you can get a bridge, which the government could do, but it would have to enumerate it, is you can do it through obfuscation. So you can connect to something that doesn't look like Tor, and then it will give you a bridge node back. So you might connect to a general cloud service or something like that, and then you could get a bridge node back as well. Okay? Yeah.
I think it's also splitting the team up. I just want to ask it. Like, can a company kind of, let's say, a scenario whereby, let's say, Canada wants to block WhatsApp.
Yeah.
Is it possible for WhatsApp to figure out a way to make sure Canadian citizens still have access to WhatsApp, but that like their hands are tied? There's nothing to do about it.
Right. Okay, so let's say you're a country, you want to block something. There's the first thing is, how do you sort out that traffic from other things? There's two basic ways. Sometimes all traffic for an application runs over a certain port number. Then you just block that port number. Now WhatsApp will change their port number. Yeah. The second thing is if they use sort of packets or things that look like that are custom, like they have a custom protocol. Now I have to run deep inspection. So with a port number, I'm seeing it anyways. My router sees it. I don't have to open the packets up and go digging. Now I do have to go digging, but if I dig far enough, then I'll see that, oh, this protocol looks different. So then the main the main thing to change there is to obfuscate the protocol, so it looks like something else. Then that's usually how it happens. So like there, I grew up in the the 90s and the 2000s, and we all pirated music using Napster and file sharing and things like that. And ISPs would shut off ports, and they would do packet inspection and things like that. And so the file browsers would obfuscate or use encryption, and you could customize your port number and things like that to try and evade that type of stuff. Yeah. Okay, other questions about Tor?
I don't have a question. I just wanted to say, like,
Yeah.
from my experience, like, if you're not tech savvy, like, if you don't have the bridge, you can actually use a snowflake, like a pluggable transport. So it's like WebRTC. You just have to do it with your browser.
Right. Yeah, so that's the obfuscation, one of the obfuscation mechanisms. Yeah. And that works, yeah. Yeah.
So you said the first and the last node are usually the most vulnerable one.
Yeah, sorry, let me say something about that. Thanks for bringing it up. Okay. Let's say you want to be a Tor node. Okay, so like, for example, Concordia, as far as I know, doesn't run a Tor node, but the university I did my PhD at does. Okay, so they want to be a Tor node. What's the vulnerability of being an entrance? We call this an entrance node. The entrance node has a lot of sensitive data. So it knows all the user IP addresses, and these are vulnerable users, usually that are using Tor. And it will have to keep track of that at least temporarily just to do its job. Okay? And so there's a bunch of privacy considerations with being an entrance node. Okay? You don't necessarily know what these users are doing on Tor, but you have all of their identity.
So the adversary will mainly target entrance node?
Not necessarily. I'm just saying that if you want to volunteer to be a node, if you're an entrance node, you have to think through the fact that you're collecting very sensitive information.
So that's what I was going to ask. Like, even if it's not a government or something like that runs the node, how do you know that the person that's running it is like trustworthy?
You don't at all.
You're sort of just leaving it.
You're sort of leaving it to chance. And also, I think the Tor people themselves will only let certain nodes be entrance nodes. And I think it's kind of based on, like, they sort of know the people and things like that. So there's, I think, a bit of social, like, intelligence that goes into it. But
the person that's running it, they could check stuff and maybe like be a whistleblower or something.
Yeah, exactly. Yeah, there is that chance. Yeah. And then what's the danger of being an exit node? Okay, so there's two things. So one is there's the information that's going back and forth, so I can see all of that. But the big problem is it looks like I sent the traffic I'm the last node. So whatever the user is accessing, it looks like I'm the one that's accessing it. Okay? So Tor is used a lot for illegal things, right? And so let's say that this is like a police server that they set up as a sting operation, and they're just trying to see who comes and accesses the server. Anyone who goes over Tor, it's going to be the exit node's IP address that gets shown up, okay? And then the police are going to go to the exit node, and they're going to, knock down their door and try and figure out what's going on. Now, the police are sophisticated now. They know about Tor, so they probably wouldn't do that anymore. But you can see news articles from 20, 30 years ago when, people were getting their doors kicked down because people were accessing, say, child pornography over Tor, and they were running the exit node that was serving up that traffic. Yeah.
In that case, is there any way to backtrack, like from the Concordia, you were selecting where is the IP address which was hitting the Concordia server. Then you were going to that node. Then you have to find which IP address hit that one. Then you can backtrack to that node.
Yeah, so if you're law enforcement, what you're going to do is you'll go to the exit node. They'll say, I'm just a Tor exit node. And you'll say, okay, where were you getting the traffic from? They'll point you at node 2. And then node 2 could point you at node 1, and node 1 could point you back to Alice.
So you can backtrack that way.
So that you can do that in theory. On paper, yes. Okay, but there's going to be two problems that you have. One is that they're not going to keep logs. So eventually you'll get to node 2, and they'll be like, that was a week ago. I don't know anymore. I knew at the time, but I didn't keep a log. Or what's going to happen is you're going to bounce from the Netherlands to Argentina, and you're the police, you're the Dutch police, and you don't have a warrant in Argentina, so you can't go get the log from this person to backtrack it back. Yeah.
If you can actually backtrack it, there's like this detail that when you go to new onions, Tor actually changes the size of your screen. So they can never, it's arbitrary, so they can never actually say that, okay, this is the ratio of your screen being smaller, bigger.
Okay, we'll get to the onion construction. So save that point till I'll show you the construction. But yeah. Yeah.
Say for instance, that if you use a VPN before the entrance to the network, does it make your traffic less private, right? In the sense that entrance nodes that they are verified by the top positions, any node can be used as an entrance node.
Yeah.
So if you have a VPN before it, and you say there's an investigation, your records could be subpoenaed from the VPN server.
Correct. So
That's your IP address and all the information.
that's right. So let's say law enforcement. So replace the word bridge with VPN. It's basically this picture. What does the VPN know? Well, it knows that you're Alice. It knows your IP address, and it knows you're talking to Tor, because it can see that this is a Tor IP address out of the Tor directory. So it knows you're one of the users who happens to be on Tor right now, but that's all it knows. So as long as there's thousands of other people accessing Tor at the same time, it doesn't know that you're a particular user or not. But it can know that you are a user that is accessing Tor.
Say, a chance of there's a chance that actually they know you are the one accessing Tor, right?
Yeah.
Is it more secure to have a VPN before it or not?
So it does add, yeah, it's kind of like adding a fourth node, right? So like I say, when you pick 3 nodes, that's arbitrary. You could pick 4. So a VPN plus 3 nodes or 4 nodes, it's the same kind of threat model where you now have 4 parties that you have to compromise instead of 3. Yeah. So the fact that this is this a bridge? Is it another Tor node? Is it a VPN or a proxy? That story doesn't really add security or subtract security. Yeah. It's just you do get added security for the longer your chain is, the more security you have, period. And then, yeah, whether that first one is, it doesn't really matter what kind of node that is. Does that make sense? Yeah. Okay. Okay, so now what I want to do is I want to set this tunnel up. Okay? But I want to set it up in such a way that this node only knows where it's getting traffic from and where it's going. And this node, even though all the traffic that flows through this node will ultimately go to node 3 and to Concordia, this node is not allowed to know that. Okay? Even if it does deep inspection. Okay? So what I'm going to do conceptually, I'll try and draw it in a way that, let me use the highlighter. Okay. What I'm going to do is I'm going to make kind of like a secure tunnel between me and node 1. Once I have that secure tunnel in place, I'm going to make a second secure tunnel inside that outer tunnel from me to node 2. And once I have a secure tunnel between me and node 2 that's through the tunnel between node 1, I'm going to make another secure tunnel inside, and it's going to go all the way to node 3. Okay? And so if you look at the traffic here, what I'm doing is I'm kind of encrypting it 3 times. I'm encrypting it for node 3 first, and then I'm putting that inside an encryption to node 2, and I'm putting that inside an encryption to node 1. Okay? So if I take a look at this packet, it kind of looks like I have my data, and it's kind of like encrypted under a key. I'm going to write the key backwards. So it's encrypted for node 3, and then that's encrypted for node 2, and then all of that's encrypted for node 1. And then every node's going to kind of strip off a layer of encryption. It's going to look at it, and then it's going to put it to the next person. They're going to strip it off, and then eventually it's going to get where it's going. Okay? Because this kind of looks like an onion, we call it an onion.
That's the logo, right?
Yeah. So the Tor logo is of an onion. And Tor used to stand for the onion router. So we call this, the whole process we call onion routing. Now Tor just stands for Tor. They kind of dropped that, but that was the original. Okay, and so what we're going to do is we're basically going to do a Diffie-Hellman, and then we're going to do another Diffie-Hellman, and then we're going to do Diffie-Hellman. But every Diffie-Hellman we do is going to be encrypted with another layer of encryption kind of thing. Okay, so I'm going to write it all out, and we'll try and follow along what happens. But before I write it out, is there any questions about overall what we're trying to do?
Is there any chance to change the word?
To change which? Sorry, the...
change the word, change the route to the destination?
So that's something that we should try and protect against. So in the protocol, we should, whatever the user chooses should be the route, and there shouldn't be a chance for the adversary to change it. Yeah. Now the nodes themselves, I think, could change it. No, yeah. What will happen is the nodes could try to change it, but it's going to fail because basically, like say this node decides to redirect it here, this won't have the key to decrypt it, and because it doesn't have the right key, then you'll end up with a route to somewhere, but the person can't decrypt and they're never going to respond to you, and so eventually it will just kind of break down. Yeah.
So the bridge is the pathway between the 3 nodes?
Bridge is just a hop before you get onto Tor. That's optional. So what I drew here is not using the bridge itself, but a bridge is just like if the whole Tor directory is banned in a country, what do? And so you,
VPN that bans it.
yeah, so you can use a VPN or a bridge.
Remember when you tried to log into the Concordia network?
Yeah.
That also didn't allow it, right?
So yes, yeah.
So then you have to use the bridge.
Exactly. Yeah. So if you try and access Tor from Concordia, it's blocked. So I do this in my other class, and then you can get a bridge through Snowflake, or for different things. Yeah.
I have a silly question. Like in the Tor browser,
Yeah.
in one chat you have opened, like you are trying to access the Concordia.
Yeah.
So the route is like, let's say the route that you have drawn is like that, and in another tab you have opened another website.
Yeah.
So the route should be like the same way, or it would change the path.
Yeah, so it's a browser configuration issue. So it's up to the browser itself. But what the browser will do, because it's expensive, you're going to see the crypto. It's expensive to build this path. What it will do is it will use that path for all traffic for a window of time. I think it's 10 minutes. So it will set this up for 10 minutes. whatever tabs you go, you don't even have to open a new tab. Remember, if you go to one website, you're going to load the images from other websites and you're going to pull all this stuff together. And so, so it's going to all go over the same circuit, essentially. Yeah. So we call this a circuit. It will establish a circuit. You'll use it for about 10 minutes. Then it will pick a new circuit. And then, that's the default behavior.
It automatically choose the shortest path.
Exactly. It won't go by shortest. It will go more by like trying to get you in different countries and things like that. Yeah. So it's picking a path more for like legal reasons rather than efficiency itself. Yeah. Okay, questions? Okay, let's look at the handshake then.
So it's only the Diffie-Hellman, no other algorithm.
So you'll see, but it's just Diffie-Hellman plus encryption. Yeah.
And the keys are generated by the pseudorandom generators.
The keys, anything client side, any key will be from a pseudo-random number generator.
So it's 3 keys, because if it is 3 nodes, then they do 3 encryption, one by one, like this, so they require 3 keys.
There'll be 3 keys, one for each node.
Yeah, and for the encryption?
And for the encryption, you'll use those keys, but that key will come from a Diffie-Hellman key exchange.
Okay.
But the exponent, like when I send G to the A, I chose a random using a pseudo-random number generator. And when the server sends G to the B back, the B was also chosen in that way. So you can think of A and B as kind of like keys as well, if that makes sense. Okay. Okay, the other thing I'll note is that we assume that we have TLS already between each node. Yeah.
Just curious, has anyone ever tried connecting to all the nodes in top just to access a place? And like, how was it? Like, has anybody ever tried that before, like connecting to all the nodes?
Oh, I see. I don't know. I don't know the answer to that. It would be very slow. Yeah. So I think there's like 1,000 nodes or something like that. It might not even let you do it, but yeah. By the way, I didn't finish my story. For Waterloo, the University of Waterloo, they run a Tor server. So they didn't want to be an exit node because they didn't want like law enforcement coming. And they didn't want to be an entrance node because they didn't want to take data off of users. So they run a node, but they're strictly only a middle node. So they'll never be an entrance or an exit. So Tor lets you do that. So they let you, when you volunteer to be a node, you can choose whether you want to be an entrance, yes or no, and whether you want to be an exit, yes or no. Entrance nodes are also like protected. So like there's a whole program to get enrolled as an entrance node. And so they don't just let anyone be an entrance node. So it's highly protected, but anyone can more or less be a middle node at least. Yeah.
Either protected and trusted for the network?
For the entrance ones, so I think there's a trust element there, but when I tried to look it up, it sounded more like it was a performance thing. So I don't know the answer exactly. In my mind, I used to always say in class it was based on trust as well as performance, but I might be wrong on that. It might just be strictly a performance thing. But yeah.
So is it just having a server running, the specific software that has to be run on it?
Yeah, so you'll run Tor. So it's going to do this custom protocol that we'll talk about. And then that's it, yeah. Yeah, and you have to have a lot of bandwidth because lots of people are going to connect between you.
Is it a big server?
Yeah, so you think of it like a pretty heavy duty server, like a web server, yeah. It's not like a machine that's in your closet. I have a spare desktop, I'm going to run Tor on it. Yeah, probably. Tor will also select, it won't send more traffic to you. It does a lot of measurements of everyone's performance and things like that, and that also goes into how it sets up circuits. Okay, let's try and get through this handshake, otherwise it's going to take a while. Okay, I'm going to assume that I have TLS between each nodes. That doesn't really help me because if I send, hey, I want a packet to go to Concordia, N1 will decrypt it, and then it will know the packet's going to Concordia anyways. Okay, so TLS just sort of protects a person in the middle between these nodes, but it's not going to give me what I want, which is okay, so what I want is I want N1 to know, it's allowed to know Alice and N2, but it doesn't know N3 or the server. So we'll have a server over here. And this can be many servers over the course of a connection. N2 is allowed to know N1 and N3, and N3 can know N2 in the server. And then they can't know anything other than that. Okay. So what Alice is going to do is she's first going to get a secure tunnel to N1. And the way that looks is just like any other protocol that we've studied. So they're going to do Diffie-Hellman. And so she's going to pick a secret. I'll call it A1. A here means it's Alice's secret. And what she's also going to do is she's going to make some random IDs, because the nodes, they're handling traffic for like 1,000 users or something like that. Okay, so when traffic goes in and when traffic comes back, they have to match it up. Like there's 1,000 people sending them traffic and it's going to 1,000 different places. Now traffic comes back and it's got to figure out, okay, was that from this user or from this user or this user? It might not know the user, it might know which node, but it has to like it's being multiplexed, okay? So the way we handle that is we assign every circuit an ID, and Alice chooses it. It's just a random number. So I'm going to call this a circuit ID, and we'll just call it 1. So this is Alice's circuit ID, and it's long enough and random enough that it's going to be unique across all Tor users at a given time. Okay, so she'll send this, and she'll send G to the A to node 1. And what node 1 can do is it can, in its like sort of database, maybe I'll write it over here. What node 1 right now is it knows that any traffic it sees that's marked with circuit ID 1 belongs to Alice. So this is its sort of temp log, temporary log. Okay, then what node 1 will send back to Alice is it will complete the handshake. So it's going to send G to the B, and it's going to send a signature with its key on G to the B. Where does this key come from? It's going to come from the Tor directory. Okay, so when Alice chose the nodes, she chose node 1. She knows that from the directory, so she knows its IP address and it knows its key. The directory is trusted. So how do I know any of these keys? Like, how do I know any of the node's keys? We don't have certificates. We don't have certificate authorities or anything like that. We have the Tor directory. So this is a different way of binding keys together with identities. It's the simplest. You just have a trusted directory, but it only works for sort of small ecosystems like this, where everyone sort of knows each other and you have thousands of nodes. It doesn't work for like the whole web because there's too many things for a directory to keep track of. Okay. All right, now what both Alice and node 1 can do, I'll write it like this. Alice and node 1 is they can get the key. And it will be G to the AB. So that's just standard Diffie-Hellman. This operation, because it's kind of long to write out, I'm going to replace it with KDF. Okay, so in the future I'll just write KDF, but it basically means the same thing, which is you run it through an extractor and then you run it through KRG. Okay, so at this point, we'll pause here and just say that Alice and N1 have a secure tunnel now. And let me call this K1 because we're going to have more than one key.
Basically, N1 is the entry node.
Sorry?
Basically, N1 is the entry node.
Yeah, N1's the entry node. Yeah. Okay, so far standard Diffie-Hellman, right? Okay, now we want to go to N2. Is Alice directly connected to N2?
No.
So she has to go through N1. Can N1 know who N2 is?
Yes.
It can, because it needs to know where to forward the information to. Okay. If Alice establishes a secure key between herself and N2, should N1 know what that key is?
No.
Okay, so what we want is, we're okay for N1 to know that she's establishing a key with N2, but we want it so that N1 doesn't know what that key is. Okay, so if Alice and node 2 do Diffie-Hellman, does node 1 in the middle learn what the key is? No, that's the property of Diffie-Hellman, right? You can have a man in the middle, and it's not going to learn the key, even though it sees everything. Okay, so here the man in the middle is the other Tor node. It's going to see everything, but it's not going to know what that key is at the end of the day. Okay, all right, so what Alice will do is she's going to send messages to N1, and N1 is going to forward it to N2 on her behalf. So now she has an encrypted key with N1. They have a secure tunnel. Okay, the encryption is K1, the key. So what she's going to do, yeah.
So, could you please go on?
Yeah.
It is really necessary to know N1 that who is N2, because
Yeah.
it can be anything.
So you eventually, because I want to route traffic through here, N1 is going to have to forward it to N2. So it's going to have to know who N2 is. Otherwise, it doesn't know who to forward it to. Does that make sense? But what we don't want is we don't want it to know who N3 is. Yeah. Okay. All right. So I'm going to start using encryption. I'm going to encrypt under K1. So node 1 can decrypt this. All right. And what I'm going to do is I'm going to say my circuit ID is 1, just so that, because node 1's getting a bunch of traffic, so it needs to identify my traffic. And I'm going to tell it the next node I want you to connect to is N2. Okay. Then I'm going to say pass on to N2. So this is just, I'm sort of putting this in brackets just for structure, but it doesn't really matter. I'll put in square brackets. What goes in square brackets will kind of look like, it's going to look like what we sent before. So what I'm going to do is I'm going to send the circuit ID for the second hop. Okay, so I have a circuit ID. So circuit ID 1 is kind of like the traffic between me and N1. I'm going to have a circuit ID for the traffic between me and N2. And eventually I'll have a circuit ID for the traffic between me and N3. So I'm saying go to N2, tell N2 that the circuit ID between N1 and N2 is circuit ID 2. And I want to do Diffie-Hellman with node 2. So this is the G to the A that I'm going to choose to do Diffie-Hellman with node 2. Okay. Then what N1 will do is it will decrypt that because it can. Okay. And well, first it's going to be like, okay, who do I give this to? I don't know who I give this to. Okay. But once it decrypts it, it will see that, oh, I'm supposed to give it to N2. Okay. So it will say, okay, I'm going to send this to N2. And I'm going to send CID2. And I'm going to send G to the A2. All right. then what N2 will do, oh yeah, and by the way, it's also going to update its database. Okay, so N1 log. It now has the same information. It knows that everything that's tagged CID1 is coming from Alice, but it also knows that this is the key that I have with Alice. Okay, so I know that. And now it also knows that anything that's coming over this circuit ID is being relayed to CID2, which corresponds to node 2. Okay, so this is the information that it keeps temporarily just to do its job. Okay, now N2, does N2 know who Alice is?
No.
It doesn't. All it knows is CID2, and it knows who N1 is. Okay, so it wants to talk to Alice now. It's going to do it through C1. Okay, and so what it's going to do is it's going to send back to N1. So it's going to mark it with CID2. It's going to send its Diffie-Hellman key. I'm using B here. B is like the server, like for Bob. But anyways, this is B1. This corresponds to the first notes. So it's going to send G to the B2, and it's going to sign it. The key that it signs it with is going to be N2, and it's going to be out of the Tor directory. So this is what stops N1 from sending it to another node. Is eventually this is going to reach Alice, and Alice is going to check the signature, and she's going to make sure that it's N2's key that signed this as opposed to another key. Okay, so now it goes to N1. So N1 looks at this. Okay, this is what N1 sees. It sees a Diffie-Hellman, and it sees a signature on the Diffie-Hellman. It knows it's getting it from N2 anyways. How does it figure out that it needs to send this to Alice? Oh, okay, so it knows it's marked with CDID2. It goes into its log, and it says, everything marked with CDID2 that I get from N2, which I just happened, that is going to Alice, with tagged with CDI1, encrypted under key K1. Yeah, so now it can fill in Alice's name. It knows where it's going. It can encrypt it. And it can encrypt all of this stuff. It can drop CDID2. It doesn't, Alice doesn't need to know that anymore. So it can just do G0. Sig K, G to the B2. And if it wants to, it can tag it with CID1, but you don't really have to do it anyways because it's going directly to Alice. There's not, usually you put the tags in because it's going to go 3 hops down the line and everyone has to track it, but it could do that if it wanted. Okay, so now what Alice and N2 can do is they can come up with a key themselves. So we'll call this K2, and it's going to be the KDF of Alice's second secret with the server's second secret. Okay, so Alice now has a secure tunnel between her and node 2. And node 1, even though they were in the middle listening to the conversation, they don't have access to that tunnel. Okay, the other thing is node 2, at this point, it receives this CID2. So node 2 here should also log CID2 is the connection between it and node 1. This log is the same as this log. Okay, so at this stage, N1 made this log. At this stage, N2 is making this log. It's the same log. It's just that N2 is about this ID in this node, and N1 is about this ID in this node. Okay, node 2 will eventually update their log to match N1's log here. Okay, all right. Then we're going to do the same process again. Okay, so we're going to now encrypt it all the way to N3. It looks exactly the same, but I'll just write it out. Okay, so Alice is going to send something to node 3, but she has to send it via node 1 and via node 2. Okay, so what she's going to do is she's going to start doing encryptions inside of encryptions. So she's going to encrypt the first layer for K1. It's going to have CID1. Then it's going to have an encrypted payload under K2. And this is going to be marked with CID2. And then this, she's going to say, okay, I want you to make a secure tunnel to N3. I want to do Diffie-Hellman with N3. The ID I want you to use is CID3. And here's my Diffie-Hellman for node 3. Okay. This packet, CID2, N3, CDI3, you've already seen this packet. It's the exact same thing that was sent here. Okay. It's one layer deeper in the encryption. That's the only difference here. Okay. All right. N2 is going to look at this. N1 is going to look at this. It's going to decrypt it. It's going to see CID1. It's going to go say, what do I know about CDID1? Oh, that came from Alice with K1. Okay, so I'm happy now. I can decrypt it. And that I need to send to N2, and it has CID2 with it. Okay, so but right now the thing, because Alice has marked it with CID2, that's fine. It's just going to send it off to N2. So it's going to strip off the outer layer of encryption. It's going to be left with the encryption of encryption 2, which has CDID2, N3, CID3, G to the A3. And it knows that I have to send that to N2. Okay. N2 is going to look at this packet. It's going to be able to decrypt it. It's going to say CDID2. Do I know that? Oh yeah, CDID2 is the thing that I'm getting from N1. So that's all good. I'm supposed to send this to N3. So it's going to send it to N3. And it's just going to send G to the A3 and CDI3. Then, yeah.
What's CDID exactly?
It's just it's a unique ID. It's a unique number that marks each link.
So from where we get it?
Alice chooses it. So Alice will choose it randomly. Yeah, so it's just a random number chosen by Alice, just so that you can keep track of what traffic belongs to which. Yeah, so when I'm getting traffic in this direction, anything marked with CDID2, I replace and update it with CDI3. When I'm going in that direction, I'm going to get traffic back the other way. And so if I get back and it's marked CDID3, then I'm going to remark it as CDID2 and send it. Yeah. Okay. All right. So we have this. Now N2 can update its log. So N2 knows that it has CDID 2. This is coming from N1. And it knows that I'm gonna derive a key between me and Alice And sorry, I'm confusing myself here.
It will be N3 log, no?
Sorry, this is N2's log. Sorry. Yeah, we'll do N3's in a second. So N2 will know we have CD-ID2. We're getting it from N1. It already knew that. But what it now knows is it has a K2. Okay, so it can add the K2. And it knows that this traffic is going to N3. And it's when it goes to N3, it's going to be given CID3. Okay. Then N3 will complete the Diffie-Hellman and send it back to N2. So it will choose G to the B3, and it will sign it. Key comes from the Tor directory. And even though I'm writing K in each case, they're different keys. So this is the key that belongs to. So I should maybe say that this is K3. And we can call this K2 because it belongs to node 2. And we can call this one K1. Okay. Then what we're going to do is, we'll just sort of do the reverse. So N2 will receive the packet. Where is it going? Well, it's marked with CDID3. I know CDID3. When I receive stuff from CDI3, I need to mark it with CDID2, and I'm going to use K2 to encrypt it. Okay, so I'm going to put CID2, and I'm going to encrypt using K2, and then I'm just going to pass on the message. And I know I'm supposed to send it to N1 because that's in my log. Okay. N1 is going to look and see CDID2. It says, I know CDID2. I pass that on to Alice with CDID1, and I encrypt with K1. Okay. So it's going to send CDID1. It's going to encrypt everything with K1, which is everything is the encryption of this with K2. Which is G to the B3. Sig under K3 of G to the B3. Do I have enough closing brackets? I need one more, I think. Okay. And then finally, Alice will decrypt everything, and she'll be able to, her and N3 will both be able to compute G to the A3, B3, and we're going to call that K3. Okay, so now Alice has a shared key with it. Okay, node 3 will update its database. And say, okay, I see stuff marked with CID3. It's coming from node 2, and I'm using K3 when I see this stuff. Now, it doesn't, all of them had, like the next node after N3 is the website itself. Okay, how it keeps track of that, we'll just say that somehow it remembers where the traffic goes and comes from. Okay, so this is the handshake. Handshake's done. Let me just quickly write out what it means to send data back and forth, and then we'll call it a day. But I just want to get it in the notes because if we do it next class, we're just gonna have to remember all of this stuff. Okay, so we'll go Alice to N1, N1 to N2, N2 to N3, and then N3 will forward it on. So it's going to look exactly like this. So you're going to encrypt under encryption 1 with CID1. Then you're going to encrypt under K2 with CID2. And then you're going to encrypt under K3 with CID3. N3. And then you're going to have your packets here. So that could be TLS packet, HTTPS, whatever. I don't care. It can be any data packet. Okay. N1 will just take off that first layer of encryption. Because they can see CDID1, they recognize it as needing to go to N2. So that's how they get the N2. So the N2 comes from this. This tells them N2. Okay. And they get rid of that encryption. And then they're just going to send off this. Okay. Then the next node does the same thing. It decrypts it. It gets ID2, so it knows that ID2 gets sent to N3. And so it's just going to send this. Okay. And then N3 will decrypt it. And it has the packet. It will send it off to the website or do whatever. The packet itself will tell it. It will be an HTTPS packet. It will have some information about what it's supposed to do. Okay. And then when the website responds, it's going to go to N3. So the website will send a response back. And what N3 has to do is it's got to get it back to Alice. Okay. So what it's going to do is it's going to say, I need to send it to N2. And when I send stuff to N2, I use CID3. And I encrypt things with K3. Okay. And then N2 to N1 will do the same, and N1 to Alice will do the same. Each of them will add a layer of encryption. So this will be CID2. The encryption under K2. And the thing I'm encrypting is this. Okay, so I put that inside. And then I do the same thing here, CID3. I encrypt under K1. And the thing I'm encrypting is everything I just received. And actually, when I do this, I can, if I want to, I can drop the C IDs. I don't have to include them.
Would be CID3 or CID1?
Sorry, say again?
The last one.
CID1, yes, sorry, thank you. Okay, and let me just, I'm just going to get rid of this because we don't need it. And then we'll have the encryption under K2 of the encryption under K3 of the response. Alice can decrypt that and get out the response. And we're done. Okay, sorry, I went over, but I just wanted to get this all here. I'll talk about it. I'll talk about the security properties next week. But yeah, thanks.